the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students who've just gone through the concepts of column spaces and null spaces, and possibly linear transformations in terms of vector spaces. We now enter really a very important topic in linear algebra. Specifically, we're going to tie in our old concepts of linear independence with a new concept called a basis. And you can see I've written right here, first concept, we now ask the question, what is the set of vectors that span a given vector space most efficiently? Because we've dealt with vectors that span spaces, and in fact, if you want to have a set of vectors span, let's say r cubed, I'm going to tell you right now, this set of vectors will span r cubed, but it's way too many vectors. You actually don't need this many vectors to span r cubed. We just have a lot of fluff here. In fact, we could say at least two of these vectors are redundant. And that's what I mean by what are the vectors that can span our vector space most efficiently. We'd like to reduce the number of vectors in our spanning set down to the minimal number of vectors necessary to span our space, while at the same time maintaining the fact that our vectors actually do span the entire space. So that's really what we want to do. We want to optimize here. The second concept is more about where this video is going to go and how it's going to feel for you. Recall that when you learned series in integral calculus, you had to reframe all of your old definitions and theorems concerning limits to fit with sequences and series. So for example, you had learned back in Calc 1 that the limit as x goes to infinity of the sum of two functions, and maybe I should write this down. So you've learned back in Calc 1 that this is true as long as these limits exist and are finite. However, when you entered into Calc 2 and you started dealing with sequences and series, you had to reframe that entire definition of what a limit was to fit sequences. And again, that would be true as long as those limits exist and are finite. Now back in Calc 2, when you reviewed those limit laws, you likely felt as though, well, this is basically like limits of functions, so it's the same definitions, whatever. They're not actually the same exact definitions, there are subtle differences between them, but you use a lot of your old theory and a lot of your old definitions to build your new theory and your new definitions. Well, that's the same thing that we're going to do here. We're going to talk about a lot of the old stuff that we've already built in this course, but this time in terms of vectors within vector spaces. So let's go ahead and see what I mean by that. And again, it should seem very familiar to you as we go through. For example, linear independence and linear dependence. The old definitions were in terms of just a set of vectors being linearly independent if the vector equation that you see there only has a trivial solution, and they'd be linearly dependent if there was a non-trivial solution to that equation. Now that we're working with vector spaces, we just include the extra little phrasing. Let V be a vector space, and suppose those vectors are from that vector space. We say those vectors are linearly independent if the equation that you see right here has only the trivial solution. Nothing's really changed, so don't think that I'm throwing something at you that's like a curveball or something brand new. It's not really brand new. We just have to modify our definition to be inclusive of vector spaces and vectors from vector spaces. Before I leave this page, I do want to mention here that the vectors we were given before, those were vectors in Rn or Rm, just depending. But now that we're dealing with vector spaces, they don't actually have to be from Rn or Rm. We've actually seen examples in our lectures where our vector spaces are sets of functions. And those sets of functions could have very specific properties, like polynomials of degree less than or equal to 2 over the real number system, or the set of all continuous functions on the interval from 0 to 1, or something like that. So we are no longer talking about vectors from R cubed or R10 or something like that, but instead we're now considering any vector space that we're working with. So I guess that is a very strong distinction between the linear independence definition we had before and what you're seeing here. Language-wise, there's hardly any difference, but concept-wise, there is a difference. For example, if our vectors are functions, then we can't build a matrix here to represent this vector equation. So let's go ahead and move forward and see what else I'm going to throw at you. Now, all these theorems are on this page by themselves because there's actually another theorem beyond this, but these theorems I grouped together because they are theorems we've seen in the past. They're all older theorems that I'm just reminding you of. For example, an index set is linearly dependent if and only if it's not linearly independent. We already know that. It's one or the other, right? You either have a set that's linearly independent or it's linearly dependent, but it can't be both. Another theorem from the past. A set of only one vector is linearly independent if and only if the vector is not the zero vector. That is actually a theorem from the past, but this might be useful in our conversations in this video and future videos concerning vector spaces. The next theorem, a set of two vectors is linearly independent if and only if the vectors are not multiples of one another. Now remember, this is kind of important because we are no longer talking about vectors from R2 or R3 or something like that. So for a simple example, very quick, suppose our set of vectors is the following. And you look at that and you say, those aren't vectors, those are functions. Yep, but they're also vectors. So our vectors are sine of x and e to the x. That's our vectors from our vector space. Well, it's not really a vector. Well, it could be from the vector space of all functions. There we go. And if I said, is this set of vectors a linearly independent set or a linearly dependent set? You would say, well, a set of two vectors is linearly independent if and only if the vectors are not multiples of each other. And I can tell you right now, there's no multiple of sine that I could do to become e to the x. Now I should say, by the way, there is a solution to that equation, but sine of x cannot, via a scalar multiple, become exactly like the function e to the x for all x values. That's just not possible. Sine of x is an oscillating function, e to the x is never oscillating. So because these are not multiples of each other, that set is linearly independent. So there you go. There's your first kind of example of our new world, our brave new world of mathematics, where vectors are no longer just vectors in R cubed, R4, or R5, but instead they're anything we want them to be, specifically for us in mathematics, functions. All right, continuing on, the very last theorem there, any set containing the zero vector is linearly dependent. That will be incredibly helpful as we move into very abstract sets of vectors. Now this theorem I kept on its own page because it's actually new to us. Sort of. I didn't really make a big stink of this in our previous work, but now I should probably talk about it. So this is called the characterization of linearly dependent sets. A set of two or more vectors is linearly dependent if and only if some vector within the set is a linear combination of the preceding vectors in the set. That we already knew from many conversations, but I never really formalized that by writing that down. I've just stated it, but now we know. If I give you a set of vectors, whether they're represented as functions or not, and if you can find one of those vectors that can be written in terms of the others, then you know you have a linearly dependent set. And a little bit of a warning before we continue forward. Now that we're not just dealing with vectors in Rn, forming a homogeneous equation such as ax equals 0 is pretty much impossible. Again, because our vectors are likely to be functions, and so building a matrix with them might be very impossible or challenging at least. So the question of linear dependence will rest solely on the true definition of linear dependence and the linear dependence relation, which is just the equation that we deal with when we're trying to prove linear dependence. So let's see that in action. Is the set of vectors from the vector space F. Remember, the vector space F is the vector space consisting of all functions. And I went ahead and tacked on that it's all functions over the field of the real numbers. That is, they're real valued functions. They could have coefficients of real numbers and arguments of real numbers. So again, is the following set of vectors, which are picked from that vector space, linearly dependent? Well, remember, it would be linearly dependent by the last theorem if I could write one of those vectors as a linear combination of the other two. We'll start by letting the vectors v1, v2, v3 be defined as follows. So they just are, there are three vectors there. And we happen to know that the cosh, or the hyperbolic cosine, is e to the x plus e to the negative x over 2. Therefore, v sub 3, which is the hyperbolic cosine, is 1/2 v sub 2, which is e to the negative x, or e to the x, sorry, plus 1/2 v sub 1, which is e to the negative x. Because one of our vectors can be written in terms of the other two, the set must be linearly dependent. And that is by the previous theorem, which is a characterization of linearly dependent sets. Now, I'm not really going to cite that or name that in our example. If you wanted to, or if your professor forces you to, you can. I just think that it's pretty easy. Just say, well, look, one vector is a linear combination of the other vectors, therefore the set is linearly dependent. I think that's good enough. And keeping with the theme that I've recently had in my videos where they're somewhat shorter than my previous videos, not by my choice, it's just by how I happen to organize the sections, let's finish out this video with this last example. Is the set of vectors from F, again, which is the vector space of all functions, real valued functions, is this set linearly dependent? From that theorem we just had written down, it would be linearly dependent if and only if one of those vectors can be written in terms of the other, as a scalar multiple of the other. Now this is where things get kind of wonky, I think, for a lot of students, because they're a little gun shy about what they want to say. They know what they want to say, but they don't know if they'll be marked off for saying this. So here's where I'm allowing you a lot of freedom. You are not allowed to make assumptions about linear algebra. Everything in linear algebra you do have to prove or use theorems that you've been introduced to show your work, that type of thing. But once you step foot into a prerequisite course full of material, it is assumed that you know all that and you can make any statement that's true that you want from that course without proof. For example, I'm currently considering this set from linear algebra of two functions, and I want to show whether or not this set of vectors is linearly dependent. Now let me remove the brackets there and talk only about the trig functions. So I start with from trigonometry, which means I'm stepping into my trig material and I'm allowed to use anything I know without proof from that course. And from that course, I happen to know cosine cannot be written as a scalar multiple of the sine. Technically, you can write cosine as a function of the sine. And it's really only a function if you know that cosine is positive or that cosine is negative. Otherwise, if you don't know that cosine is only positive or that cosine is only negative, then it technically is not a function, but whatever. So we do have a relation that we can write cosine in terms of sine, but it's not a scalar multiple of the sine. It's actually the square of the sine stuck within a square root, and there's even a plus or minus on there. So that's a very complex relation between the cosine and the sine. But for linear dependence or independence, you're only worried about scalar multiples of your functions, not square roots, not e to the powers of your functions, not natural logs of your functions, but just your raw functions with constants in front of them. There's no way from trigonometry, I know this, there's no way that cosine is some scalar times a sine. Therefore, the set we've been handed must be linearly independent. Remember, it's linearly dependent if and only if there exists a vector within your set that can be written in terms of the other vectors as a scalar multiple, as a linear combination of the vectors in the rest of the set. That's not the case, so this set must be linearly independent. Now with small sets, this is very easy to do, but once you start getting larger and larger sets, it's hard to find those exceptions, but we'll see them in future videos. But for now, we're at the end of this video. So I hope this was a gentle introduction or reintroduction to these topics, but from a new perspective, specifically vector spaces involving vectors that are not just from R cubed or R4 or R squared or something like that. So I hope this helps you in your course. I hope you have a great day. Be a wonderful human being.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry. Don't whine. Just